the pattern selection in partially filled radial weakest fringe, and I am Xu Hanyu.
Terrain.
I'm from.
And actually, open to see a lot of phenomena that show similar pattern but drive by different force, like lighting and weakest fringe. So we are wondering why. And we found that they all belong to a system called Laplace growth system, which the potential distribution in space is determined by the Laplace equation. And the growth direction will be pointing to the greatest change of the potential. But it doesn't satisfy us. We still want to further study about this pattern. And in our idea, we think this self-similar pattern can be simplified by some rules. And our idea in our study, we would like to find out those rules and find out the reason of those rules.
So our fluid system is called viscous fingering and also called second-order stability. And as shown in the left figure, when a low viscosity fluid like air inject into a high viscosity fluid, this will occur. And for this system, we just mentioned that it will obey Laplace equation. So we can derive this using some basic properties. For example, the average velocity in z direction here, and this velocity will directly proportional to negative gradient p. And for an incompressible flow, the expression is expressed as the divergence of velocity field equal to 0. So if we substitute the velocity relation in, we can get our Laplace equation. And in order to know the physics behind this phenomenon, we need to first know how a pressure is transmitted within a fluid. So for a high viscosity fluid, you can imagine there is a high friction between the fluid particles, so the pressure will decay very fast. But for a low viscosity fluid, there are barely any friction between fluid particles, so the pressure is almost the same everywhere in the fluid. So in our system, there are air acting as the low viscosity fluid, pushing into the glycerol, and when the interface is without perturbation, the pressure on the air side and the negative gradient P on the glycerol will be the same. But when there is a tiny perturbation, you can see that there is less fluid trailing behind the concave region in the glycerol. So according to the velocity relation here, we can know that the concave region will move faster than the others, so this perturbation will increase. And furthermore, in many studies shown that the capital number will play an important role in this phenomenon. For example, the capital number is defined as viscous force divided by surface tension, and this is directly proportional to the flow rate. So if the capital number is high, then the finger bifurcation will be intense.
Okay, and then we come to our experiment setup of the shell cell. In our shell cell, we use two arc to create the cell, and inside the cell, the gap is satisfies the two-dimension assumption. So, and in our experiment, we will just first inject the 10 milliliters glycerol in our cell, and then we will continue to inject a constant flow air into our cell to create the pattern. And this is our experiment video, and we can find out that it's partially filled in the initial condition. And also, we will inject constant air flow like this way.
And then let's move to the result and discussion. First, as we just said, our goal is to study the rule of the pattern. So we would like to try to simplify those patterns, those very complex patterns, to some basic unit like here. So we define a field in here, like this. It will be the fields of our basic unit. And it basically constructed by two parameters. The first one is opening angle, which is the opening of this field. And in order to simplify the curvature of the bottom of the field, we define the base width W0 to simplify that. And besides, in order to connect these two fields, we try to analyze when this finger will be splitting. We also collect this one, the finger splitting width. This following we would like to talk about.
So in order for the basic unit to work in our patterns, we need to make sure that this pattern is uniformly distributed within this our experiment. So we collect all fingertips position in theta direction, and we found out that it is normally uniformly distributed in the theta direction. So the basic unit is good. So the first parameter of our basic unit is opening angle. And if we zoom in the field, we can define this opening angle psi as if we walk a small step in the center line dl. How much is the width increase, which is dw. So the psi is arctangent of dw over dl. And if we collect the whole pattern's field, we can see that there are two peaks in opening angle distribution. And the first one is already be discovered in others' experiment. And their experiment is on a 40 field helical cell, but the second peak is different in our experiment. So we further analyze it, and we found out that this 80-degree peaks is almost generated by the developing field, which means that the center line of the field is very small. And we just mentioned that Kaplan number will plays an important role. So we measure the flow across different flow rate, and we see that the two peaks have almost no change. So this indicates that this peak is the geometry identity of this pattern.
Okay, after we talk about the result of opening angle, we are going to expand it. And in our experiment, we use two methods to confirm the opening angle. In method A, the series solution, we collect the shape of our experiment, and we'll have the shape of the pattern, and we can just solve the Laplace equation we'll just solve the Laplace equation to get the numerical series of our experiment. And we can see this picture. In this picture, the blue arrow is the gradient P in our interface. And in method B, we're using the experiment data to try to get the velocity of interface, and also we can calculate the gradient P in our interface to confirm the method A. So we can get the result is when the forward equals to 10 degrees, we can get the result is inside the forward the gradient P will become 0, like here, and it will be stable, so it will just stay in 10 degrees. And when the forward is still developing, we can find out that in two methods, the gradient P will not be 0 and not be stable. So it will just going to become 10 degrees forward before and after. Okay, and then we can go to next part of the unit, base width of forward. We can see this picture is what we researched about. And in this page, we'll talk about how we define and calculate the base width of forward. We can focus on the center line of forward, and we can focus on the linear part of forward base forward center line and trace it back to L equals 0. That is our base width. Okay, and this page, we'll talk about the result of base width. In our result, we can find out that the base width peak will focus on 0.2 to 0.3 cm. And also, we can find out that the probability concentration will just be spread out when the flow rate becomes lower. And also, we find out that the Highly correlation of base width with flow rate is not found in our experiment.
Next, we move to the final parameter of our base unit, the width of finger splitting. And how do we collect it? It's collected by a time series of film. So we track every splitting event and track the film before that. So we can find out the width of when the finger will be splitting. And the result is basically the peak of the probability distribution of our width will be concentrated on 1 cm. And the width is basically consistent on all different flow rates. And it indicates something like our system is actually a system that keep in unstable moves to unstable, unstable move to stable, and which will be affected by the perturbation. And this is the condition of when the finger will be affected again by the perturbation. It is in the 1 cm, when the finger is 1 cm.
So after basic unit, we need to discuss how the finger splits. So what we gather is that we can see there are two circled fields, circled, and this is, we trace back in time and get the first generation of field. And the yellow is their center line, and the angle between them is phi, we define as first angle. And we can see that there are a trunk between the two center lines, so we gather the tip amounts and divide it by the length of this trunk. So if we plot these two parameters in, we can see that there is a weak correlation between them. And we can interpret this by first generation. Since the first generation is purely determined by the initial perturbation, so this indicates that the amount of lateral generation is mostly determined by the first angle side, and which suggests that the degree of splitting is mostly determined by the initial perturbation.
In conclusion, so we collect basically more of our basic unit of geometry. The first one is the opening angle will be stable at 10 degrees for any fully developed field. And the undeveloped field will be 77 degrees. And for the base width, the PDF peak will at 0.3 cm, and the concentration will positively correlated to the flow rate. And the finger speed will be focused on 1 cm. And the first angle will show the impact of our initial perturbation.